These 5 objectives will be covered in 2 parts. At the end of this part 1 video, you should start to be able to define and give general equations for synthesis, decomposition, single displacement, and double displacement reactions. Classify a reaction as a synthesis, decomposition, single displacement, double displacement, or combustion reaction. List 3 kinds of synthesis reactions and 6 kinds of decomposition reactions. List 4 kinds of single displacement reactions and 3 kinds of double displacement reactions, and predict the products of simple reactions given the reactants. Thousands of known chemical reactions occur in living systems, in industrial processes, and in chemical laboratories. Often, it is necessary to predict the products formed in one of these reactions. Memorizing the equations for so many chemical reactions would be a difficult task. It is therefore more useful and realistic to classify reactions according to various similarities and regularities. This general information about reaction types can then be used to predict the products of specific reactions. There are several different ways to classify chemical reactions, and none are entirely satisfactory. The classification scheme described in this section provides an introduction to 5 basic types of reactions: synthesis, decomposition, single replacement, double replacement, and combustion. Later in this course, you will be introduced to categories that are more useful in classifying other types of chemical reactions. In a synthesis reaction, also known as a composition reaction, 2 or more substances combine to form a new compound. This type of reaction is represented by the following general equation. A plus X reacts to form AX. A and X can be elements or compounds. AX is certainly a compound.
Carbon dioxide and water can react to form sugar and oxygen. This is an example of a synthesis reaction. 2 substances have combined to form a new compound, sugar.
One simple type of synthesis reaction is the combustion of an element with oxygen to produce an oxide of that element. Almost all metals react with oxygen to form oxides. For example, when a thin strip of magnesium metal is placed in an open flame, it burns with a bright white light. When the metal strip is completely burned, only a fine white powder of the magnesium oxide is left. This chemical reaction is represented by the following equation on the screen here. 2 magnesium solid plus 1 oxygen molecule in the gaseous form react to form 2 magnesium oxides in the solid form. The other group 2 elements react in a similar manner, forming oxides with the formula MO, where M represents the metal. The group 1 metals form oxides with the formula M2O, for example, Li2O, again on the screen here. The group 1 and 2 elements react similarly with sulfur, forming sulfides with the formulas M2S and MS, respectively. Examples of these types of synthesis reactions are shown on the screen here. Some metals, such as iron, combine with oxygen to produce 2 different oxides. For example, we can have iron 2 oxide and iron 3 oxide. In the production of the first reaction, in the product of the first reaction, iron has an oxidation state or a charge of 2+. In the product in the second example, iron has an oxidation state or charge of 3+. That particular oxide, the particular oxide that is formed, depends on the conditions surrounding the reactants. Nonmetals also undergo synthesis reactions with oxygen to form oxides. Sulfur, for example, reacts with oxygen to form sulfur dioxide, and when carbon is burned in air, carbon dioxide is produced. In a limited supply of oxygen, carbon monoxide is formed. Hydrogen, molecular hydrogen, reacts with molecular oxygen to form dihydrogen monoxide, which is better known as water, and the reaction and the equation for which is represented at the bottom of your screen now. Most metals react with group 17 elements, the halogens, and they form either ionic or covalent compounds. For example, group 1 metals react with halogens to form ionic compounds with the formula Mx, again where M is the metal and X is the halogen. Examples of this type of synthesis reaction include the reactions of sodium and chlorine with potassium and potassium with iodine. One example of which is shown on the screen here. Group 2 metals react with the halogens to form ionic compounds with the formula Mx2. Again, an example right now is shown on the screen here. The halogens undergo synthesis reactions with many different metals. Fluorine in particular is so reactive that it combines with almost all metals. For example, fluorine reacts with sodium to produce sodium fluoride. Similarly, it reacts with cobalt to form cobalt-3 fluoride and with uranium to form uranium-6 fluoride. Sodium fluoride, which has the formula NaF, is added to municipal water supplies in trace amounts to provide fluoride ions, which help prevent tooth decay in the people who drink the water. Cobalt-3 fluoride, which is COF3, is a strong fluorinating agent, and natural uranium is converted to uranium-6 fluoride, which is UF6, as the first step in the production of uranium that is used in nuclear power plants. Active metals are highly reactive metals. Oxides of active metals react with water to produce metal hydroxides. For example, calcium oxide reacts with water to form calcium hydroxide, an ingredient in some stomach antacids, the equation for which is represented on the screen here. Calcium oxide, again represented as CaO, which is also known as lime or quicklime, is manufactured in large quantities. The addition of water to lime to produce calcium hydroxide, CaOH2, which is also known as slacked lime, is a crucial step in the setting of cement. Many oxides of nonmetals in the upper right-hand portion of the periodic table react with water to produce oxyacids. For example, sulfur dioxide, which is represented as SO2, reacts with water to produce sulfurous acid, according to the equation represented on your screen here. In air polluted with SO2, sulfurous acid further reacts with oxygen to form sulfuric acid, one of the main ingredients in acid rain. Certain metal oxides and nonmetal oxides react with each other in synthesis reactions to form salts. For example, calcium sulfite is formed by the reaction of calcium oxide and sulfur dioxide, according to the equation at the bottom of your screen here. In a decomposition reaction, a single compound undergoes a reaction that produces two or more simpler substances. Decomposition reactions are the opposite of synthesis reactions and are represented by the following general equation, again represented on your screen here. AX reacts to form A plus X. AX here is always a compound, but A and X separately can be either elements or compounds. Most decomposition reactions take place only when energy in the form of electricity or heat is added. Examples of several types of decomposition reactions are given in the following sections of the course. The simplest kind of decomposition reaction is the decomposition of a binary compound into its elements. We have already examined one example of a decomposition reaction, which is the passing of an electric current through water as it decomposes the water into its constituent elements, hydrogen and oxygen, according to the equation on the screen here. The decomposition of a substance by an electric current, like the equation on the top of your screen, is called electrolysis. electrolysis, splitting with electricity. Oxides of the less active metals, which are located in the lower center of the periodic table, decompose into their elements when heated. Joseph Priestley discovered oxygen through a decomposition reaction in 1774 when he heated mercury to oxide to produce mercury and oxygen, according to the equation at the bottom of your screen here.
Electrolysis is the use of an electric current to cause an oxidation-reduction reaction. Electric current is the passage of electrons. Because oxidation is the loss of electrons and reduction is the gain of electrons, the passage of electric current through a solution causes these reactions. For example, when current is applied to water, the hydrogen in the water is reduced to elemental hydrogen, and the oxygen is oxidized to elemental oxygen. Because 2 moles of hydrogen are formed for every mole of oxygen, twice as much gas is formed in one tube as in the other. When the electricity is shut off, the reaction stops. Electrolysis is also used in electroplating.
When a metal carbonate is heated, it breaks down to produce a metal oxide and carbon dioxide gas. For example, calcium carbonate decomposes to produce calcium oxide and carbon dioxide, according to the equation at the top of your screen. All metal hydroxides, except those containing group 1 metals, decompose when heated to yield metal oxides and water. For example, calcium hydroxide decomposes to produce calcium oxide and water, according to the equation in the middle of your screen now. When a metal chlorate is heated, it decomposes to produce a metal chloride and oxygen. For example, potassium chlorate, which is KClO3, decomposes in the presence of the catalyst MnO2. It produces potassium chloride and oxygen, according to the equation at the bottom of your screen now. Certain acids decompose into non-metal oxides and water. Carbonic acid is unstable and decomposes readily at room temperature to produce carbon dioxide and water, according to the equation at the bottom of your screen here. When heated, sulfuric acid, as another example, decomposes into sulfur trioxide and water. And sulfurous acid, which is H2SO3, decomposes in a similar fashion. At this point, you should be starting to be able to define and give general equations for synthesis, decomposition, single displacement, and double displacement reactions. Classify a reaction as a synthesis, decomposition, single displacement, double displacement, or combustion reaction. List 3 kinds of synthesis reactions and 6 kinds of decomposition reactions. List 4 kinds of single displacement reactions and 3 kinds of double displacement reactions. And predict the products of simple reactions given the reactants.